Some days you want to do repair work, and some days you just want to space chat about SPI communication. SPI stands for Serial Peripheral Interface. It's a communication protocol for electronics. Electronic communication protocols are rules that set how two or more devices transmit information to each other. Wi-Fi or USB are more commonly known communication protocols, but SPI can be really good for things like DIY projects because it's simple and it uses less hardware and system resources. SPI uses serial communication where bits are sent one by one across a single wire. Bits are sent or received in a continuous stream instead of being sent in packets like with I2C or UART communication, so there's less data interruption. Not using start, stop, or acknowledge bits like you do with I2C gives you almost double the data transfer rate. SPI devices utilize controller-peripheral relationships. A single controller device, something like a microcontroller, controls one or many peripheral devices like a display or a sensor. It uses 4 wires, the MOSI line, which sends data from the controller to the peripheral, the MESO line, which sends data from the peripheral to the controller, the clock line, which is just the line for the clock signal, and the peripheral select or chip select. This is the line the controller device uses to select which peripheral to send data to. Depending on how new your SPI device is, the MESO or MOSI lines might say COPI and CIPO instead. This is because controller peripheral is updated terminology to replace the old master and slave terminology. The controller sends data in serial, so bit by bit along the MOSI line. Usually the most significant bit is sent first. The peripheral can send data back to the controller bit by bit through the MESO line. Usually the least significant bit is sent first. Data can be sent and received at the same time since SPI uses both of these lines. Communication protocols can be synchronous or asynchronous. Synchronous is when both devices share a clock signal. The clock signal synchronizes the output of data bits. One data bit is transferred per clock cycle, so the frequency of the clock signal determines the speed of the data transfer. SPI is synchronous, and the controller device can modify the clock signal using clock polarity and clock phase. The clock polarity states whether the clock is idle when high or low. The clock phase states whether data is shifted in and out on the rising or falling edge of the data clock signal. The chip select line is at a high voltage when it's idle and nothing is being transmitted to or from the device. The controller device then selects which peripheral it wants to talk to and switches the line to a low voltage level. First, the controller outputs the clock signal. The controller then switches the chip select pin to low, which activates the peripheral. The controller sends the data bit by bit to the peripheral along the MOSI line. The peripheral reads the bits as they're received. If the peripheral needs to respond, it returns the data bit by bit to the controller along the MESO line. The controller also reads the bits as they're received. In the Arduino platform, the SPI library is already included, so you don't need to install it externally. To code a new SPI device, you need to know a couple things about it first. The maximum speed your device can use. This is controlled by the first parameter in SPI settings. A 15 MHz chip would use this big number as the speed. Arduino will automatically use the best speed that is less than or equal to the number that you use with SPI settings. If the data is shifted in the most significant bit or least significant bit first, this is controlled by the second parameter in SPI settings. Most SPI chips use most significant bit first. If the data clock is idle when high or low, and if samples are on the rising or falling edge of clock pulses. These modes are controlled by the third parameter in SPI settings. There are 4 modes of transmission for the clock polarity and clock phase. This table from the Arduino documentation on the SPI library shows the mode for each. So now we've got an idea of the basics of SPI communication. It's a fast 4-wire serial communication protocol for electronics. If you want to see Arduino tutorials where we put things like this into practice, check out my channel where I've got beginner level projects set to the theme of fixing this broken spaceship we're in. And you don't want to be stuck floating aimlessly in space, do you?